right, using first and second order integrated rate laws. So first things first, you have to work out if the particular question is following first order or second order kinetics. And I can see here it mentions first order kinetics. So we are going to use the integrated rate law for a first order reaction. Okay, so the integrated rate law for any first order reaction where rate equals K times the concentration of A to the power of 1, so just that, is going to be ln of A at the time in question that we're interested in is minus KT plus ln natural log of the initial concentration of our reactant A. So in this case, our reactant is this Cl, CH2, CH2, Cl, etc. Well, that's a mouthful, isn't it? And we're asked to find the concentration 24 seconds later. So we are solving, I'm sorry, we are solving for AT, concentration at time t. The complicating factor is these natural logs. So rearranging something with a natural log in it, ln of something minus ln of something else is just going to be we can just divide them, right? So we're going to have ln of the the concentration at time t divided by the concentration at t equals 0 is going to be minus KT. So we're going to rearrange like so, and then we can do e to the power of both sides to get rid of that pesky logarithm. So e to the power of natural log ln is just the thing that you're natural logging. So I didn't mean to go all the way along like that. That's talking for you. And then we'll end up with e to the minus KT on the right hand side. So e to the power of both sides is going to give me A at time t over initial concentration equals e to the power of and then minus KT. Okay, so then if we multiply both sides by A0, then we'll end up with our rearrangement equation rearranged solves A at time t is the subject. You could also be excited and just plug and chug, but then you're going to end up with your answer of natural log of the answer. So you have to just remember to take the exponential of that to unlan it, if you like, whatever you prefer. So we should be able to plug into this equation and solve for our concentration at time t, which is 24 seconds later. So let's do it. I'm going to leave myself plenty of space here. So e to the power of, and then minus KT, so minus K, and I'm going to put the units in 0.0764 per second, so that's second to the minus 1, times t, which is 24 seconds. So you can now see that that power of E will be unitless because per second and second is going to cancel out. And then that is going to be multiplied by our initial concentration in molarity, which was 0.200 molarity. So our units are going to come out in terms of molarity. So that will be E to the power, I'm going to do it again like this so it's easy to see, of that should shake out to be minus about 1.84 blah 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 and friends times 0.200 molarity. So notice I've left off the units now for E because the units cancel. So e to the power of minus 184. I'm doing this step by step just to make sure you can check if you're putting this into your calculator. Obviously, I'll just put it all into my calculator and use parentheses liberally, but there you go. So that should shake out to be about 0.1598 times 0.200 molarity, which is going to give me a number for my molarity of 0.03196 blah 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 molarity. We're asked for two significant digits, so the two significant digits, that'll be 0.32 molarity, or 3.2 times 10 to the minus 2.